Today we're going to prove Birkhoff's theorem in general relativity in the case where we have an electromagnetic field and a cosmological constant. So the theorem states that in this theory the only spherically symmetric solution is given by the Reissner-Nordstrøm-de-Sitter solution. There's a special case when the electromagnetic field is absent and the cosmological constant is 0, then we get the Schwarzschild solution, which is the usual version of the theorem. We're going to take a differential forms approach to the problem. First up, let's introduce a connection. Now, the connection be A, we can have the covariant derivative d, which is little d, plus rho A. So we have a Lie algebra corresponding to a Lie group, capital G. A is a Lie algebra valued 1 form. Little d is the exterior derivative. And rho is a representation of the Lie algebra appropriate to whatever we are applying the derivative to. So for instance, if we have something in the fundamental representation of the Lie algebra or Lie group, so we have alpha in there, then d alpha is just d alpha plus a wedge alpha. If we have f in the adjoint representation, then df would be little df plus a wedge f minus f wedge a. That'll be useful later on. An example of a Lie algebra will be SO13, and we'll come on to that in a second. That will be equivalent to investigating the frame bundle. But you might also have SU2 if, for instance, you were considering solutions to a space-time with an SU2 gauge field. Now we're going to define gauge transformations by dGA plus GD, so this should be alpha. Alpha, where this thing is D plus AG. So G here is an element of the Lie group. So for instance, if alpha was a vector and G was a rotation, then this would be mapping to another vector. Just seeing how the covariant derivative transforms under this change. Well, I can write this out. That's dg wedge alpha plus g d alpha plus ag wedge alpha. You can swap the wedge product and the g essentially they're in different spaces. This is g d alpha plus a wedge alpha. Those cancel. And since alpha is arbitrary, put a g on it, GA would be G inverse dg plus g to the minus 1 ag, and that's known as a gauge transformation. At least in physics. Next thing we'll do is look at the curvature. The curvature is given by applying covariant derivative twice. So d squared applied to alpha, alpha being in the fundamental representation again, that's equal to d alpha plus a wedge d alpha d alpha plus a wedge alpha plus a wedge d alpha plus a wedge alpha. D squared is 0, so that gives me dA wedge alpha minus a wedge d alpha. Note the minus sign because of the anti-symmetry of the wedge product. So a wedge d alpha nicely cancels. A wedge alpha, and that's f wedge alpha, where f is equal to dA plus a wedge a. Now a wedge a is not 0 because in general A is an element of the algebra, and elements of the algebra generally don't commute. Let's investigate the gauge transformation of the curvature, or the field tensor, as it's sometimes known. Fg wedge alpha is gd squared of alpha, and that's gd squared g to the minus 1g alpha. Using this property here, that's gd g to the minus 1d g alpha, and that's equal to g to the minus 1 d squared g alpha, and that's g to the minus 1 fg wedge alpha. Since alpha is arbitrary, curvature transforms this way, and that means that f lives in the adjoint representation of the algebra. Now let's have a look to see what happens if we apply d 3 times. I can write that as d squared d alpha, so that's f wedge d alpha. But it's also equal to d squared alpha, and that's df wedge alpha, and that's df wedge alpha plus f wedge d alpha. Note the plus sign, remember f is a 2 form. So that implies that df is 0 since alpha is arbitrary, and this is the Bianchi identity. We can see this explicitly from this formula here. If we look at df, that's d of dA plus a wedge a plus a wedge dA plus a wedge a minus dA plus a wedge a. I'll bring this into view in a moment. The cubic terms in a go away. This thing d squared is 0, so we get dA wedge a minus a wedge dA plus a wedge dA minus dA wedge a is 0. Okay, let's apply this to the case when G is SO13, and we consider a frame, so EA is an orthonormal basis with metric given by eta here. Elements of the algebra will be antisymmetric matrices once we lower both indices. So that's eta AC omega CB, omega AB is minus omega BA. That will be an element of the algebra. Now, DEA, elements of this frame, that's 0 if we're looking for a torsion-free connection. So of all the connections which are consistent with the metric, one which is torsion-free is the Levi-Chittifer connection. And when you first come across general relativity, you assume the Christoffel symbols are symmetric in the lower indices. That was the condition that the connection is torsion-free, and it translates in this case to this condition here. So that is given by, if we now say D is D plus omega, in this case will be given by DEA plus omega AB wedge EB is 0, which is one of Cartan's structural equations in the absence of torsion. Let omega be the curvature. So that's d omega plus omega wedge omega, or in components, d omega AB plus omega AC wedge omega CB. So A and B here are the algebra indices, and these things here are only goes to one form, so that term and that term are both two forms. Now, this thing we can write out as sum c less than d of r, a, b, c, d, e, c, wedge, e, d, because these form a basis for the space of one forms. That's a half r, a, b, c, d, e, c, wedge, e, d, where this tensor here is antisymmetric under the change c swaps with d. So this is the Riemann curvature tensor. And r, a, b, c, d is minus r, a, b, d, c. Because of this, and when I lower this, this is supposed to be elements of the algebra, so that's also minus r, b, a, c, d. Okay, let's apply d to this equation. So d squared ea is 0. That's omega wedge ea 0, or omega ab wedge eb is 0, which implies that r, a, b, c, d are antisymmetrized. e, b, e, c, e, d is 0. So r, a, b, c, d is 0. Now if I use this condition and these ones up here, I will also, it's a very small calculation, show that we have this result here, swapping the first pair of indices with the second pair of indices, symmetric under that change. The Bianchi identity is then RAB, C, D, semicolon, E is 0. We won't be using that. Now let's consider a metric. Let G equal ds squared be equal to minus a dt squared plus 2b dt dr plus c dr squared plus r squared d theta squared plus sine squared theta d phi squared. Here a, b, c are functions of r and t. So this is the general form for a spherically symmetric space-time. R is the radial coordinate such that the surface area of a sphere of radius r is given by 4 pi r squared. That determines the r coordinate. Now we can always find the function d, say, such that this thing can be written as proportional to d of something, d little t. So it's just an integrating factor. In which case, minus a dt squared plus 2b dt dr, that's dt times dt plus 2dr, so that's dt plus b dr, and that's equal to minus a to the minus 1 d squared dt squared plus a to the minus 1 b squared dr squared. So making this change essentially gets rid of this term here in the metric. So I can write ds squared equals e to the minus 2 nu dt squared is e to the 2 lambda dr squared. It's r squared d theta squared plus sine squared theta d phi squared, where nu is nu of r and t, and lambda is lambda of r and t. I could redefine t by any function of t, and we will use that freedom later on in the calculation. Now I'm going to introduce an orthonormal basis, so I'd like E0 to be equal to e to the nu dt, E1 is e to the lambda dr, E2 is r d theta, and E3 is r sine theta d phi. Okay, we'll put those to one side for a second, and now consider the question of spherical symmetry. Let's consider the two-dimensional metric, which is the round metric on the unit sphere. I want to know what the killing vectors of this metric are. So the killing vector satisfy lead derivative of g with respect to k is 0. I'm going to write k as k theta d by d theta plus k phi d by d phi. We need to work these things out because we need to know that the magnetic field should be invariant under spherical symmetry, and so we need the lead derivative of the field with respect to the killing vectors of the metric here to give 0. Right, the lead derivative k is ikd plus dik. It's the inner product with k. So lead derivative of d theta is d squared 0, so get dik d theta, and that's dk theta, and so that's k theta comma theta d theta plus k theta comma phi d phi. So the lead derivative of d theta tensor d theta is going to be lead derivative of k d theta tensor d theta plus d theta tensor the lead derivative of k d theta, which gives me twice k theta theta d theta tensor d theta plus k theta phi d theta tensor d phi, and that should be the symmetrized product. So A symmetrized tensor product is a half A tensor B plus B tensor A. I would have been using the notation d theta squared and d theta d phi in other contexts, but it's worth writing this out in detail. Lead derivative of the following thing, sine theta d phi, is ik d sine theta d phi plus dik sine theta d phi. That's ik into cos theta d theta wedge d phi from there, plus d sine theta k phi. And this gives me cos theta times k theta minus cos theta k phi d theta, and there should be d phi in there, plus cos theta k phi d theta plus sine theta into k phi comma theta d theta plus k phi comma phi d phi. Now that cancels with that, and so we get sin theta k phi comma theta d theta plus cos theta k theta plus sin theta k phi comma phi d phi. Therefore, the Lie derivative of sin squared theta d phi tensor d phi is twice sin squared theta k phi theta d theta tensor d phi symmetrized plus sin theta cos theta k theta plus sin theta k phi comma phi d phi tensor d phi. Close brackets. So half Lie derivative of the metric is the sum of these two things. So divide by 2, k theta theta d theta tensor d theta plus that term there, k theta comma phi plus sin squared theta k phi comma theta and again sin theta cos theta k theta plus sin theta k phi phi d phi tensor d phi. So I want this thing to equal 0, so I need k theta comma theta to be 0. So k theta I'm going to write as f prime of phi. Prime is going to be useful for later on. We'll need, from this equation here, we're going to get cos theta k theta plus sin theta k phi phi is 0. Or in other words, k theta is minus k phi phi is minus f prime of phi cot theta. So k phi is minus f of phi cot theta plus g of theta integrating up. Finally, we need to solve this thing equal to 0. So that tells me that f double prime of phi plus sin squared theta times the derivative here, that gives them a cosec squared, so that cancels out with that. Phi plus, I should move this to the other side, minus g prime of theta times sin squared theta. So I need to solve this equation. Well, this is just a function of phi and this is just a function of theta, so that must be equal to some constant. Now, were I to change f goes to f plus a constant, then that won't change the value of this quantity here, k theta. And if I also change g, goes to g plus c sin squared theta, cot theta, then that won't change this thing here either. So I can use this freedom to essentially assume that that's equal to 0 and g prime of theta sin squared theta is 0. So now I look for a basis of solutions. Well, let's take the first one. F is 0 and g equals 1. So then k is equal to d by d phi. Let's call that thing x. Now assume g is 0. The solution to this will have f, actually I'll write f primed as e to the I phi. So f is minus I e to the I phi. For instance, we're not worried about constants, as I've already said. So that gives me King vector e to the I phi d by d theta plus I cot theta d by d phi. And you also have y bar is another independent solution. Now I could take linear combinations to get real solutions, but actually I'm perfectly happy having complex Killing vectors in this case. Right, let's try and apply this to the electromagnetic field. So what we're going to do is start with the assumption that the electromagnetic field tensor is ftr dt wedge dr plus f d theta dt wedge d theta plus f d phi dt wedge d phi plus f r theta dr wedge d theta plus f r phi dr wedge d phi plus f theta phi d theta wedge d phi. So that at the moment is a general antisymmetric tensor, or two-form. Now, Maxwell's equations, df equals 0 and d star f equals 0. We'll come back to that one later because it depends on the metric. We also want this field tensor to be invariant under these Killing vectors. So lead derivative of x is ixd plus dixf, but df is 0, so I just need that, and similarly to y, that's also 0. Well, dixf is equal to, from here you're just going to get minus dt phi dt plus fr phi dr plus f theta phi d theta. Since ixf, of course, is just given by pulling out the theta terms from here, here, and here, and the minus sign because it's in the second variable. So that's 0. Now, iyf is going to be e to the I phi minus sine f t theta dt plus f r theta dr minus f theta phi d phi plus I cot theta I x f, coming from that term there, in brackets. So diyf, which we know is 0, here is e to the I phi. We're going to get d of this stuff here, we differentiate this term here, which gives me an extra I d phi wedge this stuff. That term goes away. Then we get minus I cosec squared theta d theta, which IXF, plus I cot theta dIXF. And actually, that's actually equal to 0. The sign of the cot and of the cosec are wrong in this equation. So, taking the imaginary part, tells me that, well, multiply it by e to the minus I theta and then take the imaginary part, tells me that ft theta dt plus fr theta dr, that's equal to cosec squared theta d theta wedge IXF ft phi dt plus fr phi dr plus f theta phi d theta, which we don't worry about because it's d theta plus d theta term. And this should all be a d phi wedge that. Now, these are all independent, so therefore you must have ft theta is fr theta is ft phi is fr phi is 0. So the sign of the cosec squared does not change this result. What are we left with? That's gone, that's gone. Oh, that's gone, that's gone. We're only left with these two terms in f. The real part of this equation tells me that df theta phi, d phi, that's that bit, there, that should say, that should still be, that should say d phi wedge IXF times 9 cot theta. Minus sign. The plus sign was correct. And that followed from the differential of this times this term here. So that's equal to minus cot theta f theta phi d phi wedge that. This equation is now correct. Collecting these together using the integrating factor, that's d cosec theta f theta phi wedge d phi is 0. I spoke correctly, but for some inexplicable reason I've written cos instead of cosec. So that implies that f theta phi no comma is some function p of phi times sin theta. Now remember that d ix of f is 0, so that tells me that minus df theta phi wedge d theta is 0, which will imply that p is constant. Now df is 0, so from here we still have this term to think about. D of this thing, this is only a function of theta, so d of this is 0, so I have d f t r wedge dt wedge dr is 0, which shows that f of t and r is a function of t and r. So let's call that q of t and r over r squared, and have an e to the lambda plus nu just because we can. So lambda and nu, if you remember, were these parameters here. And the reason I've written it in that way is because I'm now going to write f in terms of the basis that I wrote down up here, the orthonormal basis. So we get f is q r to the minus 2 e0 wedge e1 plus p r to the minus 2 e2 wedge e3, which is q r to the minus 2 of e to the lambda plus nu t wedge dr plus p sin theta d theta wedge d phi. And now we can compute the Hodge dual of that. So we get, so from this one, p r to the minus 2 e0 wedge e1 plus q r to the minus 2 e2 wedge e3. There should be an additional minus sign in front of the p in this equation. And so, comparison of this, e to the lambda plus nu dt wedge dr plus, that's now q, which is a function of r and t. But d star f is supposed to be 0, got no problem with that. But this is only 0 if q does not depend on t and r, so therefore q is constant. So that gives me the electromagnetic field tensor, which is spherically symmetric. Now the energy momentum tensor is 4 pi TAB, 4 pi TAB is FAC, should say FAC, FBC minus a quarter eta AB, FCD, FCD. So 4 pi T00, for instance, is going to be F01, F01 minus a quarter times minus 1 times F01, F01 plus F23, F23. F01 is going to be Q over R squared. That gives exactly the same thing. Actually, that's double because you'll get 1 0, 1 0 as well. So we have plus a half into, that's minus q squared over r to the 4 because I've had to raise 0. And that's plus p squared over r to the 4. So that's z squared over 2r to the 4, where z squared is q squared plus p squared. 4 pi t11 is f10, f10 plus a half minus q squared r to the 4 plus p squared over r to the 4. Actually, that's a minus sign. Well, this is the same as this, but we had to raise a 0, so get the opposite sign. So that's minus z squared over 2r to the 4th. 4.t22 is f23 minus half minus q squared over r to the 4th plus p squared over r to the 4th. And that thing is just p squared over r to the 4th. So we're just going to get z squared over 2r to the 4th. F32 minus a half this thing. That gives me exactly the same answer as I just had. Z squared over 2r to the 4th. And all the other components are 0. Right, let's now work out the curvature of the metric. So, going back to this metric here, this frame, I'm going to have DEA equals 0. So in other words, DEA plus omega AB wedge EB is 0. E0 with e to the nu dt. So DE0 is minus e to the nu minus lambda nu prime dt wedge E1. So I've written in terms of that basic vector, which is minus omega naught a wedge EA DE1. Should have written these things out. R sin theta d phi. That thing is lambda dot e to the lambda minus nu dr wedge E0, which is minus omega 1 a wedge EA. DE2 is dr wedge d theta, which is minus e to the minus lambda d theta wedge E1. DE3 is dr times sin theta wedge d phi plus r cos theta d theta wedge d phi, which I can write as that thing minus cos theta d phi wedge E2, and that's minus omega 3a wedge EA. So I want to use this, so DEA is minus omega AB wedge EB, that's what I use there. I need solutions which are antisymmetric when I lower the leading index. Well, there's a formula for it, but I'm not going to use that. I'm going to spot the answer. So omega naught 1, this is the tricky one actually, and that's 1, get that, so e to the nu minus lambda nu primed dt, that will work. Now, when I lower this, I change its sign, and I want this thing, once it's lowered, to be antisymmetric, so actually I get the same thing here, but this thing is inconsistent at the moment. When I look into here, I would need to add on lambda dot e to the lambda minus nu dr. But then, does that make this inconsistent? Well, no, because that gives an E1 wedge E1 term. So that's worked. Let's have a look at omega 2,1. Well, minus e to the minus lambda d theta, omega 1, 2, e to the minus lambda d theta. You can see that omega 1, 2 gives a d theta. D theta term, and d theta, wedge d theta is 0. So that's nice and consistent. Omega 3, 1. E to the minus lambda sin theta d phi. Omega 1, 3. E to the minus lambda sin theta d phi with a minus sign. Omega 3, 2. Pull that out of here. Cos theta d phi. 2, 3 minus cos theta d phi, and that doesn't mean anything else. Okay, so we find out this is the connection coefficients that work. Now compute the curvature 2 form. Omega is d omega plus omega, which omega. So omega AB is d omega AB plus omega AC, which omega CB. Omega 0,1 d of this thing. So I'm just going to need the time derivatives there. Sorry, as the t terms, I actually only need the spatial derivatives, mu prime minus lambda prime minus nu prime plus nu double prime. So mu minus lambda dr, which dt, which plus term from here, which is lambda double dot plus lambda dot into lambda dot minus nu dot dt, which dr. And that's all times e to the lambda minus nu. So write this out in terms of these things here, and we're going to get e to the minus 2 nu into lambda double dot plus lambda dot squared minus lambda dot nu dot, so that term, minus e to the minus 2 lambda into nu double prime plus nu prime squared minus nu prime lambda prime. And that's 0, which E1. And if you have a 0 there and a 1 there, you would need either a 0 or 1 in there to get something 0. But actually, you then have omega 0 or an omega 1, which is 0. So that is all we have from that one. Omega 0, 2. So there's no contribution from the derivative term. So a 0 and a 2 there. A 0, 1 and a 1, 2. So omega 0, 1. Wedge omega 1, 2. So now express this in terms of this basis. We get minus nu primed e to the minus 2 lambda r to the minus 1 e naught, which e2 minus lambda dot r to the minus 1 minus nu lambda e1, which e2. So not quite right here. That should be a plus, that should be a minus. That's better. Omega 0, 3. I'll just write down the answer. Lambda r to the minus 1 e to the minus 2 lambda e1, which e2, plus lambda dot e to the minus lambda minus nu r to the minus 1 e0, which e2. Omega 1, 2. Is go the wrong one down. That's omega 1, 2. Omega 0,3 is minus r to the minus 1 e to the 2 lambda e1 wedge e2 minus lambda dot e to the minus r to the minus 1 e1 wedge e3. New prime missing there. Omega 1,3 is lambda prime r to the minus 1 e to the minus 2 lambda e1 wedge e3, and omega 2,3 is 1 minus e to the minus 2 lambda r to the minus 2 e2 wedge e3. From these we can work out the Ricci tensor. So the Ricci tensor is RAB EA tensor EB. Let's call it Ricci, just to make sure we don't confuse it with the Ricci scalar. So the components are R00, which is minus R01, 01. So you have that 0101 is just this quantity here. So you can get e to the minus 2 nu lambda double dot plus lambda dot squared minus lambda dot nu dot plus e to the minus 2 lambda into nu double prime plus nu prime squared minus nu prime lambda prime. Now 0202 is that term there, and 0303 is nothing. That's not right. That should be 03. That's 1, 3. Yeah. That's, I think, which is the same. That just gives me an extra 2 nu primed divided by r. That last term should be with a plus sign. R11 using the symmetries of the Riemann tensor is going to be that thing. So R0212 is that thing. Minus lambda dot e to the minus lambda minus nu r to the minus 1. And this thing here, 03 components. Sorry, 0313 components. Is exactly the same thing. So you get that. That was 01. R11 is R0101 plus R1212 plus R1313. So we get this expression again, and we also get 1212, that thing to add on, and 1313, that thing, so that's the same thing. So that gives me e to the minus 2 nu lambda double dot plus lambda dot squared minus lambda dot nu dot. minus e to the minus 2 lambda u double prime nu prime squared minus nu prime lambda prime and these extra two terms. So it's rather similar to what we have up there. R22 is R020 plus R1212 plus R2323. Naught 202 gives me that term. 1212 gives me that, and 2323 is that term there. So adding those up together, you're going to get r to the minus 2 minus e to the minus 2 lambda r to the minus 2 1 plus nu primed r minus lambda primed r, and r33 is r0303 r1313 plus r2323. So 0303, that pulls out that term. 1313 is that, and 2323 is that. It's exactly the same as this. So that was number. Okay, now let's consider the Einstein equations of this system. We have RAB minus half R e to AB plus e to AB is 8 pi TAB. If we contract on A and B, you get R minus 2R plus 4 lambda is 0. Since that is 0, it's traceless. So R is equal to 4 lambda. Substitute that into here and move over the side with RAB is 8 pi TAB plus lambda e to AB. Okay, we know that R1 is therefore 0, so therefore lambda dot is 0. So lambda is just a function of R. Now R00 plus R11, given that we now can get rid of all those terms are gone. That's now gone. So we just get lots of cancellation. Here we get a nu and a lambda. So we get minus 2 e to the minus lambda r to the minus 1 nu prime plus lambda prime. And that's equal to 8 pi t00 plus t11, which is 0. Remember, this was z squared over r to the 4. That's the whole thing. Plus minus z squared over r to the 4. So therefore, mu is minus lambda plus some function of time. But remember that nu came into the system as the metric coefficients here. So that's equal to e to the minus 2 lambda times e to the 2h of t dt squared. and so that's e to the minus 2 lambda, which is a function of r, times dt tilde squared, where t tilde is e to the h of t. There should be a dot over the t tilde. So had I started with t tilde instead of t, then h would have gone to 0 and nu would be to minus lambda. Right, let's have a look at the equations we need to solve. Here we're going to end up with e to the 2 nu double prime plus 2 nu prime squared minus 2 nu prime over r is equal to z squared over r to the 4th. This other equation gives exactly the same thing. This one down here tells me that r to the minus 2 minus e to the 2 nu r to the minus 2 into 1 plus nu prime r to 2 nu prime r is equal to z squared over r to the 4th. Right, let's solve this equation. So nu double prime to e to the 2 nu looks like e to the 2 nu times nu prime. All prime, if I work that out, I end up with nu double primed times if I want, but I also end up with 2 nu prime squared e to the 2 nu. So this equation here is e to the 2 nu double primed over 2 minus e to the 2 nu primed over r is z squared over r to the 4. Let f be e to the 2 nu. So we have a half 1 over r into f double primed minus f primed r there. R to the 4, factor 2 there. Let's think about the sign. No, there was a sign error here, that should be a plus. So that's a plus. So we have that. That's just a half 1 over r f double primed. You can recognise that as the, if I write f double primed plus 2 f primed over r, you can recognise that in terms of the Laplacian spherical polars, the radial component of that. So we have that equal to z squared over r to the 4. We also have the equation r to the minus 2 minus r to the minus 2 into f plus f prime r equals z squared over r to the 4th, or 1 minus r f primed is equal to z squared over r squared. Well, if I were to differentiate this equation, r f primed minus z squared over r squared, then I get r f double primed is equal to z squared cubed if I divide through by r, get 4, 2 gives me that thing, oh, there's already a minus sign, so that's that, which is this equation here. So actually all I need to do is solve this equation, and the other equation will be automatically solved. So we have that. So f, integrate that, that gives me an r, and divide by an r, that gives me 1. Integrate this thing will give me plus z squared over r, and then now we divide by another r. We're missing something, we're missing the cosmological constant. I'll come back to that and get a constant of integration, which will be 1 over r, so minus 2m over r. So for the 0, 0 term, I need to those things cancel off there, so that wasn't a problem. This thing, I should have a minus lambda here, and this thing should have plus lambda there. So that changes these equations. This one should have a minus lambda here, and this one should have plus lambda here. So we have a plus minus lambda here. Differentiating this lambda r squared lambda r squared. So if I differentiate this again, I get a 2 lambda r divided by r. That gives me a minus lambda, which is here. So actually it's still okay, but I have to solve. So 1 minus r f primed plus z squared over r squared equals plus lambda r squared. So r f primed is 1 minus z squared over r squared minus lambda r squared. So when I integrate that, I get minus lambda r cubed over 3, and divide through by an r, so we get that. So ds squared is minus 1 plus z, 1 minus 2m over r plus z squared over r squared minus lambda r squared over 3 dt squared plus 1 minus 2m over r plus z squared over r squared minus lambda r squared over 3. So minus 1 dr squared plus r squared d theta squared plus sine squared theta d phi squared. And that is the Reissner-Nordstrøm-de-Sitter solution. If the cosmological constant is 0, then we get the Reissner-Nordström solution. If, in addition, the electromagnetic charges are 0, then we get the Schwarzschild solution. So that completes the proof of Birkhoff's theorem under these conditions.